So let's look at what's happening in this problem. The ramp is at some angle theta, and here's a wire that's moving down. The magnetic field points down everywhere. So this wire moves down at speed v. So as a wire moves down, the flux in the circuit, which is given by magnetic field times area times the cosine of the angle, is changing when the wire moves down. So the induced EMF is going to be the derivative of flux with respect to time, which is this. So the current induced in the circuit is the EMF divided by its resistance. So we have this as the current induced in the wire. And the force that the wire feels is going to be I times L cross B. So we know I, L, and B. I is that. So we put I times L times B. That's a current, or that's a force that the wire feels. So the force that the magnetic force the wire feels is given by this expression. So now let's look at how these forces act. This force is acting to the right, and also we have the force of gravity acting on the wire. So the wire feels this magnetic force completely to the right. Let's look at how it would be. Here's the magnetic force, here's the force of gravity. So we want to get the component of the magnetic force along the ramp, and the component of gravity along the ramp. And those two components have to be equal because the wire is moving at a constant speed, it's not accelerating. So we just set those two things equal. We know the magnetic force, the magnitude of the magnetic force is this, and we know the force of gravity is mg. So we can just easily solve now for v. So v is just this, and that's the velocity at which the wire moves down the ramp. So this is this number once we plug in all the values.